Great. So for this part of the program, we have scheduled a discussion to really start thinking about, well, not start thinking about, but play around with the ideas of transient astronomy, high energy astrophysics in the era of the Vera C. Rubin Observatory, DSA 2000, and other facilities that are coming online at the same time. We've already met Kevin and Greg, and it is my great pleasure to introduce Krista Lynn Smith. Krista was an Einstein Fellow here at KIPAC between 2017 and 2020, right after she completed her PhD at the University of Maryland. Since then, she has moved on to an assistant professor position at Southern Methodist University in Texas, and she has recently moved to the faculty at Texas A&M. And Krista's work is all about the time variability of active galactic nuclei and supermassive black hole sources, and doing really clever things with exoplanet satellites, Kepler and TESS, for studying those. So it's a great pleasure to welcome her to the stage to join the others. So to kick this off, I just wanted to give all of our panelists sort of 2 or 3 minutes just to kind of outline what they're most excited about and what they're thinking about first of all. So I guess, yeah, Kevin, you've just got the mic, so yeah, we'll start with you.
Well, I also just gave a talk, so I gave a little bit of a preface of what I'm excited about. So.
Yes. Yes, sir.
Yeah, but I guess I'll expand a little bit beyond what I talked about. So I just told you about all these amazing LISA binaries and the synergies with what LISA will do for galactic gravitational wave sources. Something I want to bring up that I think is going to be absolutely amazing too is the just general variable star science. I mean, variable stars have been a cornerstone of astronomy for a long time, right? And we've done amazing things with Cepheids and RLRA. We're literally about to expand to a sample of 20 billion stars with Rubin and get time series for all of them. That's an enormous volume. Like, we talk a lot about the transients and the number of alerts per night, but it's worth remembering too, just the sheer expansion, the volume of number of stars, many of which won't be generating alerts because they're low amplitude variations. But if you look hard enough at any star, you can find signals in its power spectrum if you've got the signal to noise to do it. So what I think I'm most excited about is actually on the variable star side community, being able to explore that huge phase space and combine it with increasingly powerful surveys at other wavelengths, like we just heard in the radio. We've got things coming in the X-rays too, like AXIS, that has very high angular resolution. And being able to synthesize all these deep high angular resolution images at multiple wavelengths is just going to be incredible. So I think that's kind of what I'm most excited about.
So thank you, Dan, for the invitation and the introduction. Yeah, so I actually am glad to be in this group because and no offense to transients, I like transients, but you're right. There are persistently variable sources that are fascinating from an astrophysical point of view and are very much part of the dynamic universe that we're kind of moving into now. And so what I work on is very high cadence observations in the optical of jets and accretion disks. But moving forward, especially with Rubin, that there's 2 arenas of things that are very exciting indeed. And one is more the ability to do this kind of rapid cadence with big numbers of AGN and with multiple colors. And what that gives you is an appreciation for how the detailed microphysics of the accretion disk works. So the inner regions out to the outer regions and how those interface in a multi-wavelength way with rapid X-ray timing and rapid radio timing, which I'm very excited by the talk that we just saw. And then the physics of extragalactic jets and things like that are also very interesting there. On the slower cadence side, you have the ability to use techniques like reverberation to measure black hole masses, especially with the colors that Rubin will have over its 10-year run. And in that way, and at the depth that Rubin can do, we will be able to build up a black hole mass function over cosmic time that's truly unprecedented and understand the buildup of structure and massive objects from very high redshifts that we've never been able to do before. So that's going to be very exciting as well.
All right, thank you. I agree with all those points completely. And in terms of things that I think we as a community need to understand, I think Rubin's going to change everything with respect to the sheer number of alerts, events, and candidates that it's going to produce. And the question about how we find a needle in a haystack changes. So I was at Caltech and I watched Kevin do his needle in a haystack search. It was very impressive. But even 10 Kevins will not be able to find all of the things that Rubin will produce. So I think we need to make sure that we have really well thought out ways to do anomaly detection that probably involve machine learning in various different ways, and maybe moving into the foundational AI domain at some level. So I think that's going to be very important. And I think the other thing that I think the community, as other telescopes, we are doing our best to come online and overlap strongly with Rubin. And for us, there's a lot to learn, and I think Rubin will have solved a lot of the problems we will face. But there are things that become important for multi-wavelength searches for events. So in our case, for example, a lot of the slow transients we will find will be things that Rubin will have seen 3 and 4 years earlier. And we should be optimizing our cadence to maximize detection of events that Rubin is well characterized, and planning accordingly. So there's things like that, optimized cadence across wavelengths and across surveys that really aren't a problem for many surveys, but for radio and optical, it definitely is an issue. When we first tried to do slow transient searches with the VLA, maybe 10 years ago, it was a program called the Caltech NRAO Stripe 82 survey, and we interleaved PTF observations of Stripe 82 with the VLA, and we had no matches that were in both surveys because we'd done it wrong. We should have waited 2 years after doing the optical and then done the radio, right? It's obvious, but we were trying to find ways to find new things. So cadence and planning across multi-wavelengths is another thing I'm excited about talking about.
Sounds good. And you kind of touched on this already, but I wonder if just each of you could, if each of you has got maybe 1 or 2 top sort of high-level science questions, big challenges that you would like to see solved in this transient and time domain, in the Vera Rubin Observatory domain. I guess start with Kevin.
I can tell you one of the things I'm determined to find is a white dwarf in a short orbit with a black hole or a neutron star. Just given the number of double white dwarfs I'm finding, they should exist. The same physical processes that form double white dwarfs, if you have a massive enough star as one of the progenitors, should give you a more massive compact object. And we think some ultra compact X-ray binaries we see with neutron star accretors must have come from basically a detached and spiraling system. So they must exist, and especially if we find a black hole white dwarf pair, we predict things like calcium-rich transients may actually come from the tidal disruption of a white dwarf around a black hole, for example. So I think that's just a sheer numbers game of just you need to find enough ultra compact systems that statistically you're likely to run across a neutron star or black hole. So I think that's one thing where we just don't have the numbers with ZTF in the current surveys. And Rubin will really expand into the territory where you can find those. So that's one of the main science cases. And one of the interesting things I think is going to come out of Rubin too is we'll really start to get a sense of like completeness of these objects in the halo and the local volume around the Milky Way, sort of the binary period distribution, their space density. And in conjunction, something I'm working on is trying to use JWST to stare at globular clusters to see if I can find these using similar techniques. And basically compare the rates of the systems, because one of the big open questions right now is how important is dynamical formation in these compact binaries? Do all the LIGO sources come from globulars or not? I've heard heated debates about that, and I think we're actually in a position to be able to start to answer those questions.
Krista.
Yeah, so I'll mimic Kevin's way of answering. There's something I'm determined to do, and then there's something that I am excited for everyone to do. Something that I'm determined to do, Bob touched on this a little when he advertised his poster, is determine the self-similarity of accretion across the mass scale. So from stellar mass objects up to supermassive objects, because we've found some tantalizing hints that there's something wrong, like something isn't quite the same at supermassive scales, and it kind of should be. That's been the paradigm all along. So is there something about strong gravity or something about space that's off there, or is there something about our observations? And it goes back to having the numbers. We just haven't had the observations we've needed to look for these quasi-periodicities that we see in stellar mass black hole accretion disks quite often. We haven't had the baselines, the colors, and the cadences to find them in large numbers. And I think my preliminary investigations with the Rubin data seem like they will do that. And then the other one is what I touched on a little earlier. This black hole mass function, yes, they can do the reverberation, and that's good. But measuring masses with black hole masses with reverberation is subject to some assumptions that are challenging. Measuring black hole masses in general is very challenging. There's lots of degeneracies, and there are very cool ideas that myself and many others have about using machine learning to look for other binary signatures of binaries, signatures of the relationship between mass and different accretion disk properties that may manifest in the light curve. You can measure the mass ratio of binaries. So given the appropriate data volume and color scintillation and things like that, there's ways to do this in very statistically powerful methods that may give us an independent handle with less degeneracies on supermassive black hole mass measurements.
Thanks, Krista.
Okay. Yeah, there's a lot of different areas where the impact will be huge. I'm very excited to see what happens with respect to getting a better picture of pre-supernova mass loss, be it from binary interaction or nuclear instabilities, for example, because in with something as sensitive as Rubin, you will be able to actually see those bumps in the light curve, pre-supernova in a systematic way. And you're also going to see for the shells of matter that are ejected, that the ejected crashes into, for the shells that are pretty nearby, you will also be able to see those out to a great distance, because they'll be very, you'll see things like F-bots and so on. And I think there's a lot of complementarity to the radio, which is more sensitive to further out shells. And just building that picture of what's involved in stripping envelopes, and what's involved in giving you tight binary systems. In the case of binary interaction, that of course gives us we think is one of the main avenues for giving us LIGO binaries, or and so on. So that's one aspect. Another I think is resolving the question of the site of our process for once and for all, right? By having really deep systematic characterization of and searches for events, and being able to actually measure robustly the contribution of lanthanide poor and lanthanide rich ejecta at early times. And that's all that's another avenue where I think Rubin as well as IOR surveys will be very important. And then I really want to understand where FRBs come from. And I think you can't do that with radio data. You really have to be able to you have to understand what are the properties of the host galaxy, and probably more importantly, what are the properties locally to the event, right? Is it sitting on a globular cluster, which we know of one example where it is, which means that in that case, it's likely coming via for example, a merger population. Many sit on dense Notha star formation, but there's not been enough systematic study of those yet, because they haven't been enough localized. Localization will happen in the radio, but like being able to build that picture of what's the characteristic age of the population that explodes, that gives you the comet objects that we see as FRB sources, will be how we figure out how they're produced.
Great, thanks. So I'd really like to involve everyone in the room in this discussion, but I'd like to try a little experiment first, just to kind of get everyone warmed up. I mean, sometimes it can be a little bit slow getting questions and input from the audience. So I'd like everyone just to kind of chat for about 4 or 5 minutes with the people sat around them, sort of in groups of 2 or 3, maybe 4, just depending on how the seating's working out. And maybe think about, first of all, what you're most excited about, and if you have any questions based on what you've just heard from Kevin, Krista, or Greg that you would like to put to the panel. So let's take about 4 or 5 minutes just to chat with our neighbors and get some ideas flowing. Okay, hopefully we've got some ideas flowing around the room. It sounds like it's been a very active discussion. So any thoughts, any questions? Who wants to go first? Roger.
When one builds something like Rubin, the idea is to make n a very large number. But the reason why you care about that, there's two kinds of reasons. One is that 1 over the square root of n becomes a small number, so you can do statistics. Another is that 1 over n itself becomes a small number, so you can find very rare objects. In the former case, you can get a lot of science out of just the survey data. But in the latter, you've got to do a lot of follow-up to tease the physics out. Now, I'm curious what the panel thinks about, you have a variety of environments. If you're at Caltech, life's pretty easy to do follow-up. For some of the rest of us, it can be pretty tough. Do you have any comments about how we're going to live in the Rubin era and deal with the 1 over n problem?
Well, I'll start off by just saying that it requires very clever ways to discover those anomalies, because you don't know what you're looking for in the really rare things, because the rare things that Rubin sees, no one will have ever seen. And the rare things that everything else sees, Rubin will see loads of. So it's just it's a new era. And I hate to roll out the lazy known unknowns and unknown unknowns example, but that's where it really becomes. How do you find the known unknowns? And that's something that you can plan for in a more easy way. The unknown unknowns, it really is anomaly detection. And I think it relies on being able to access every data point from every telescope in as optimal way as you can in the time domain, across a broad SED, and look for things that essentially have not been detected or characterized previously, and filter those triage them into whatever resources you have at your disposal. And maybe there's some community process to be able to make sure the resources are available, because it's very hard to have vertical integration when you've got something like Rubin that's already so sensitive that building a follow-up telescope is hard.
Yeah, so that's a great question, and I until last month was at quite a small university with very little resources or access to facilities, and so for me the trick has always been to use as cleverly as you can and as resourcefully as you can all the surveys that are happening at the same time, and look ahead enough to be ready for the Rubin data that happens at the same time as monitoring patterns for tests. It would be the early example, but that will be redundant except for the cadence, but also with Fermi, with WFIRST, with any kind of survey instrumentation that's happening on the ground or in space, in X-ray imaging or X-ray spectroscopic or SLU surveys, any kind of data you can use to kind of, write that one important SWIFT proposal, that one important NICER proposal that overlaps with the monitoring of 2 or 3 other things to try and cross-correlate and find the golden egg, I guess. And that's, relying as much on public survey data as you can to target your proposals effectively.
Yeah, I'll just comment. I think there's going to have to be a cultural shift in the time domain community too. I was at Caltech and I saw plenty of people spend entire nights of Keck just 5 minutes per transient taking a spectrum to find maybe 1 or 2 exciting things that would yield a paper. That's not going to work in the Rubin era. Like, you can't take a spectrum of every 24th mag supernova candidate you have. And so I think there is going to need to be a cultural shift of like, these methods of just brute force triage are not going to work. That being said, so you develop tricks to pick out your rare object using just Rubin in the sort of large scale surveys. You still need to be able to then follow those up. So there's still going to be a huge role that, yeah, you will need the resources, and you're going to have to be stingy and make sure that you use them with high fidelity and are not trying to just brute force take spectra of everything. But yeah, that's why I mentioned in my talk, I think there's going to be a big role of taking current 5 to 10 meter class telescopes, outfitting them with better throughput instruments. They can still play a role here. Rubin doesn't saturate until 18th, so that's within access. And then, yeah, the ELTs, I think, also are going to need an instrument suite to do this sorts of follow-up. And I hate to say it, but a lot of the ELT community right now is very focused on science cases for not this type of science. And so it's on us to kind of push to make sure instruments are in the pipeline for Rubin follow-up.
Okay, so just kind of so picking up on this idea of follow-up, Greg, you talked about one of your big science goals as figuring out the origin of FRBs. Where do you think the balance lies in solving that problem between having more FRBs with detailed follow-up across multiple wavelengths, or versus discovering just a larger number of FRBs in a statistical sense? Where do you think that the balance needs to be to really move forward with that question?
For that particular question, I think it's going to rely on being able to detect as many nearby FRBs as we can, such that we can do pretty good characterization. It's very analogous to the long and short GRB problem, where things like the Fruchter examination of the the association of long GRBs with the brighter parts of galaxies that are brighter than Cork Lab supernova region, where Cork Lab supernova typically happen, as an example of how you tease that out. So I think it's going to rely on finding more GRBs, and I think it's going to rely on being more clever about follow-up resources. So for the DSA 110 FRBs, so that's detecting two a week or so, localizing them to their host galaxies. So we are using Keck resources, and Vikram Ravi is the PI of the program, and it's like it's many nights. That's not sustainable into the DSA 2000 era. So it's going to have to rely on better photo Zs, better ways to triage, and moving out of this domain of being able to, like Kevin says, you can't brute force these things with big glass the way we've done it at Caltech before. It relies more clever tools, and I think that's finding those very anomalous objects that give you a lot of information are the key thing. I'll give two examples. The first localized FRB 121102. That one event provided so much context. It's on a star bursting dwarf galaxy on not a very dense star formation. There's an associated quiescent radio source, and that's all from one source. And there was recently another FRB that's actually localized to a globular cluster, around a nearby galaxy. Those two events alone provide a huge amount of information about the pathways for progenitors for FRBs.
That's good, thanks. And from the audience, any more questions, comments, thoughts?
On that, what do you expect the redshift distribution of the FRBs to be, just very roughly?
0.5 to 1.
Okay, thanks.
Okay, Steve.
So a question from our little group of four here. You spoke eloquently at different times during your presentations to the value of randomness in your sampling and the value of coordination in your sampling across wavelengths. I'm just wondering, in this epoch of multi-wavelength surveys, how you would suggest we bring those two things together.
I'll just say one quick thing, and then I'll hand it over to the other two. I'll add one third thing as well too, which is avoiding redundancy. So what happened for GW 10.17 is like 50 telescopes try to make the same measurement, and that was okay for that event. But as we get into the industrial era, we've got to figure out how to play nice and prioritize and try to maximize the science for the community.
Yeah, well, in the terms of surveys, the nice thing is the randomness can come from surveys for free, but I think something important to think about for different science cases is matching depth and angular resolution. So I work a lot with test data that has very limited angular resolution, and honestly, that instrument's time is best spent looking at the poles for that reason. Like if you go into the bulge, you're just, it's kind of a nightmare. And so I think in building future instruments, like I'm very involved with AXIS, this X-ray imaging satellite with a very high angular resolution. And the first thing we propose for is let's do a time domain survey in the galactic bulge, where the X-ray source density is so high that E Rosita cannot resolve them. And kind of, think about each instrument and like, how can I uniquely leverage what's special about this particular detector to look at a part of the sky where it's going to maximize the impact? I don't think we necessarily do enough of that to really think about what makes this instrument unique and better at doing this. We have a lot of right now, just everyone wants to build a new time domain survey without stopping to think like, and one of their main science cases is maybe kilonova follow-up, because that's like everyone's favorite science case for an optical time domain survey, without thinking like, does my survey have an advantage over the others here? Or am I just putting this in my STM because it's a very attractive broad science case? So I think more of that thinking is important.
So this is an excellent example of how what's good for one science case is bad for other science cases. Just one of the things that has made the exoplanet satellite data revolutionary for high energy astrophysics is the perfectly even cadence, because our signals are stochastic. And anything else we want inside them is buried in that stochasticity. And sometimes we want the interesting information from the nature of the noise itself, the red noise behavior. And the windowing functions and stuff are killer when you're trying to do that. And non-Fourier or not strictly Fourier techniques are very, very difficult to understand what is signal and what is artifact. So even sampling is critical. And with the low angular resolution of tests, you might think that's bad, but actually, when you are dealing with something that's variable, but it's inside of an extended optical source like a host galaxy, big giant pixels where the whole source is inside one pixel is actually pretty nice. So the problem with TESS is the limiting magnitude, because AGN are rare on the sky, or relatively rare. They're quite faint. So bright AGN are rare. So it sort of depends. But yeah, it's apples and oranges, I think, with sampling.
So I guess a question sort of picking up on the AGN timing between mostly Krista, but sort of between Krista and Greg. I mean, we think of AGN as being sort of classic multi-wavelength sources, and you can observe them with just about anything. Have you thought at all about the value you could get combining sort of the LSST style AGN-like curves, other AGN-like curves in the optical band with what you could do in the radio with something like DSA 2000?
Yeah, so certainly there, the run of LSST is a nice span of time during which there could be lots of interesting surveys that are designed. I have thought, particularly the colors that have made it interesting to me in concert with X-ray timing, because there have been very beautiful targeted studies like the STORM collaboration stuff and some of the stuff by Rick Edelson using Swift and some ground-based things that have shown with very expensive targeted observations of a few, 2 or 3 AGN, this lovely correlated variability with a lag from hard X-rays to soft X-rays to the UV, to the blue, to the red, to the infrared. And you can map the causal relationship of the central engine very well. That has been, but those are very, very expensive, observations that are multi-wavelength, and the ability to do something approximating that beautiful work on large scales would be fantastic. The radio adds an interesting context there because I just described kind of the canonical, a corona out through the torus of the reverberation. But the radio, depending on if it's radio loud, if it's radio quiet, if the origin of the radio emission is a corona or a jet, we don't really know very much about, especially in radio quiet AGN, where that emission comes from. So putting that into that same context and on that same footing will be great.
And I have only a little to add. I don't work directly in the AGN domain. I'm always impressed with how much information you have to disentangle. But there's really important science there, and that makes it worthwhile for Krista and others to do. The experience I had was at the VLA Sky Survey, where we were finding thousands of transients, half of which typically are powered in some way by supermassive black holes. And then there's this boundary that seems to have quite a large overlap into the tidal disruption event domain. And we're seeing pretty significant samples of radio TDEs, and how you time your radio, it's almost always the case that you care, apart from things like FRBs and pulsars, that the stuff that happens at higher energies in optical are probably happening before you see things at radio, certainly in the DSA 1000 band. And it's all about trying to make sure that your radio sampling is optimized to be able to go back and say, well, This is a radio transient. It's sitting on a Seaford, but it has a lot of the behavior we expect for a TDE. Going back in the optical IR, seeing if there's an IR bump, see if there was, you know, an optical bump that gives you more evidence of whether it may have been a TDE and so on. So it's down to that sampling and optimized delay timing for the radio, I think, for the radio surveys.
Cool, sounds good. So we've probably only got 1 or 2 minutes left before lunch, and we can take another comment or two from the room, or if not, I've got one last question for Kevin, but I'll give the room a chance first. Okay, so Kevin, at the beginning, I was really interested when you said detecting black hole, white dwarf binary. How would you do that? What do you need to do that?
Yeah, so the trick is that these are called ellipsoidal variables. If the white dwarf is tidally deformed by the black hole, you'll get a sinusoidal modulation. Now, the problem is, how do you tell that it's being deformed by a black hole versus a neutron star or a white dwarf? Well, if it's not accreting, which is pretty easy to tell, because if you've got an accreting black hole or even white dwarf in an ultra compact, it's going to be a bright X-ray source. So if it's not accreting, what you do is you just watch the orbital evolution. And if the white dwarf has a black hole companion, the chirp mass is way bigger. And so it's going to have a decay rate that's much faster than the ones being deformed by white dwarf companions. And so with just Rubin light curves, that's a way of, you look for all the ellipsoidal variables and you find the one that's decaying 10 times too fast for a double white dwarf at that period. So yeah, that's an example of, like, without doing any spectroscopic follow-up to check for giant RVs, that you can just use general relativity and light curves to pick out those systems. And that's when you need GMT or TMT, because you say, okay, this is really a winner. Let's get the RVs and study this thing. So the triage is still important. You still need to do the follow-up, but yeah, you need to be pickier about what you choose to follow up, because you're going to have so many candidates. Yeah.
Cool, excellent, sounds good. Well, it's lunchtime, so thank you to Kevin, Krista, and Greg